Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Now today the topic is we are going to solve few numerical problems based on the unit transformer. Fine. Now these numericals are very important for our examination, and the numericals which we have taken for this lecture are taken from previous year's examination question paper only. So please pay attention. Okay, so let us see what is our first numerical for today's class. So first numerical says that for a magnetic circuit on no load condition, the core loss is 16 watts. Fine. So what we are going to do is we will note down all the important points. Okay. So important point is no load condition. Very good. Under no load condition, we represent the current by I naught. Then core loss is 16 watt. So core loss is given as 16 watt. Then apparent power, which is VA RMS, which is represented by E1 I0, is given by 20 VA. Okay. Then E1 max, that is the maximum induced voltage in primary, is given as 275 volts. Assuming a sinusoidal flux waveform, find power factor, iron loss component of current, that is IC, and magnetizing component, that is IM. Okay. So the very first thing is that core loss is represented by E1 into I0 cos theta C. Now theta C can also be represented by phi 0. Okay. Both are the same parameter. Sometimes we say phi 0, or in some books they refer to that parameter as phi C. Okay. So what we will do is we will convert this equation in terms of power factor. So what is power factor? Power factor is cos theta. So in this case it is cos theta C. So we have converted this equation in terms of this. Okay. So it becomes power factor is equal to the core loss upon VA component. VA component is given as 20. So power factor becomes 16 by 20, which comes out to be 0.8. So my power factor comes out to be 0.8. Okay. Now let us talk about the next thing. Now here we have E1 RMS is equal to 275. But RMS value is given by, the maximum value is given by 275. Now in AC we know that we don't bother about maximum value. We always talk about RMS value. So what is the relationship between RMS and peak value? RMS is equal to peak by root 2. Okay, so peak value is 275 divided by root 2 is 194.5 volts. So that is our RMS value of primary voltage. Okay. Yes. Now we have this equation. Okay. Now we have this equation that PC is equal to E1 into I0 into cos theta C. Now we know what is PC, 16 watt. We have calculated this also, correct? Yes. So we have calculated cos theta C, which is 0.8, and now we have E1 also, because this is RMS value. So now we have EM. So what we will do is we will convert this equation in terms of I naught, which becomes PC upon E1 multiplied by cos theta C. Fine. So this is my I naught. So my I naught comes out to be 16 upon 194.5 multiplied by 0.8, which comes out to be 0.103 ampere. So this is my no load current. Okay. Now I know that core loss component is in phase component, correct? So it is given by I0 or I0 cos theta C. I know I0 or I0 which is 0.103. I know cos theta C which is 0.8. So I can calculate the core loss component. And the magnetizing current component is in phase quadrature, right? It is 90-degree component. So that will be given by I0 sine theta C. So I0 is 0.103. Now I want theta C. So I don't have theta C. I have cos theta C. So what will be now theta C? Theta C will be cos inverse 0.8. Fine. So this value has been put here. Okay. So we got the magnetizing component of the current to be 0.062 amperes. So we have calculated all the values. I hope you understood how to solve such numerical. Fine. Let us go to the next numerical. Now next numerical says a transformer has a primary coil and secondary coil with the number of loops are 500 and 5000. Input voltage is 220 volts. What is the output voltage? Okay. So here what is given? Again let us see what is given. The number of turns in the primary and secondary is given, right? Now if you notice, the number of turns in the primary are 500 and number of turns in the secondary are 5000. It means which type of transformer is this? This is step up transformer because N2 is larger than N1. Fine? Yes. So let us solve this now. Okay? Yes. So in this case, this is N1 or NP. This is N2 or NS. This is primary voltage or V1. Now we want Vs or V2. Both are same, right? We have to calculate this. So do you remember that we have transformer ratio which is N2 by N1 equal to V2 by V1 equal to I1 by I2 equal to K. So we can use that equation here. Correct? Now, see, if I use these terminologies here, these nomenclature, I would say Vs upon Vp is equal to Ns upon Np. Okay? Now I will have cross multiplication. So my equation becomes Vs upon Ns is equal to Vp upon Np. So I will convert this equation in terms of Vs, which becomes Ns upon Np multiplied by Vp. Okay? Yes. So we will place the value and we get Vs is equal to 2200 volts or 2200 volts. Wasn't it very simple? We just have to know what is the turns ratio or what is the relationship between the number of turns and the output voltage. Now let me remind you that these questions were asked in university examination. Okay. So let us go to the next numerical now. Now the next numerical is a lengthy numerical. The first two numericals were part of the first question. So the marks assigned for those questions were either 4 or 5. Now this question is comparatively bigger question. Okay? Yes. So let us see what it specifies. It says that an 80 kVA 3200 by 400 single phase 50 Hz transformer has 111 turns on secondary windings. Calculate. Fine. So let us see what all values are given here. Fine. So kVA rating is given, which is 80. Okay. Now 3200 by 400 is given. So what does this mean? This means that this is primary voltage and this is secondary voltage. Then frequency is given 50 Hertz. Well, let us see what is the use of this. Okay. Then secondary windings are 111. It means N2 is 111. Fine. What else is given? No, we have covered everything, isn't it? Yes, we have covered. Now, just in the last numerical, we saw that E2 by E1 is equal to N2 by N1. So what are we supposed to find out here? Number one, the number of turns in the primary winding. It means we have to find out N1. So we will convert this equation in terms of N1. So we will have cross multiplication. We will take N1 here, E2 here, and E1 goes to the numerator. So N1 becomes E1 by E2 into N2. So what is E1? 3200, E2 400, and N2 was 111. Okay. So this goes off. Yes. So the number of turns in the primary windings are 888. So this is essentially a step down transformer. Fine. So let us see what is the second point. It says secondary full load current. Okay. So how do we find out secondary full load current? Okay. So for that, we need to understand the kVA full load. Okay. So again in last numerical, we had written the equation for this. If it is kVA, then it is given by E2 into I2 full load. And since it is kVA, it has to be divided by 1000. Remember in last equation, it was primary. So we had written E1 into I0 and it was no load condition. So we had written I0. This is full load condition and this is secondary full load current. So we have written I2. Fine. So here we have to find out this I2 full load. So we will convert this equation in terms of I2 full load. So this will be kVA multiplied by 1000 upon E2. So what is kVA? 80 multiplied by 1000 upon what is E2? 400. Correct? Yes. So what I will do is I will use this part. So 20 into 10. So my I2 full load comes out to be 200 amperes and my N1 came out to be 888 turns. Okay. Now the next is the cross-sectional area. The cross-sectional area of the core if the maximum flux density is 1.2 Tesla. Okay. Now do we have any equation for this? Yes, we do have. Remember the transformer equation? Yes, we have. Correct? So E2 was given as 4.44 into F into N2, correct, into phi m. Now this was the equation. Now here area is not there. But then we know that maximum flux density is what? Yes. Now this phi m is given by Bm into A, or Bm was actually flux per unit area. Okay, we know this relation. So we will replace this value. So my new equation becomes 4.44 F N2 BMA. So what is unknown? A is unknown. So A becomes E2 upon 4.44 F N2 BM. Now all other values are known. Correct? So what is E2? 400 divided by 4.44 multiplied by frequency 50 multiplied by the number of turns in the secondary 111 multiplied by the maximum flux density, which is 1.2 Tesla. Now this is an SI unit, so we will directly use 1.2 as it is. So this area, cross-sectional area, after doing the calculation, comes out to be 0.0135. What will be the unit of the area? Meter square. So this is how we found out area. Okay? Fine? Understood? Yes. So let us now go to the last numerical for the day. Now this numerical says a 40 kVA transformer has a core loss of 450 watts, full load copper loss of 850 watt if the power factor of the load is 0.8. Okay, now see, this is a different type of numerical. Fine, because now here it has full load efficiency, maximum efficiency, and the load in kVA. Yes, so this is going to be interesting. Now the first thing first, we will note down what all is given, right? So kVA is given. Okay, so I will say that yes. Yes. So in order to find the full load efficiency, what I will write here is first kVA. kVA is given as 40. Fine. Now I have an important point to make. Okay. Now core loss. Core loss is also iron loss, and we have represented in our derivations the core loss or iron loss, we have represented it by Wi. Now we can use, as I said, any nomenclature. Okay. So it is 450 watt. Now what is important point here? The important point is here we have the unit of K. So even this power has to be mentioned in K only. We cannot take the power in watts. We have to convert it into kilowatt. So it becomes 0. We have to divide it by 1000, right? So it becomes 0.450 kilowatt. Next, full load copper loss. Okay, full load copper loss. It is 850 watt. Again, it has to be converted into kilowatt. So it becomes 0.850 kilowatt. Please keep these things in your mind. Otherwise, we will be getting a different answer altogether. Fine. Secondly, power factor is given. Power factor is given as 0.8. Very good. Now, how do we write the full load efficiency? Do we have the equation for that? Yes. We have the equation for that, and the equation is this. Correct? Now let us see what all values we require for this. Full load kVA. Full load kVA, yes, we have. Power factor, we have. Again, full load kVA, power factor, iron loss, copper loss, yes. But then what is X here? Now this is very important. Okay, full load efficiency. So full load means the load is full. It means it is 100%. So the value becomes 1. So here the value of X becomes 1. Okay. Now we shall put the value. So the efficiency, percentage efficiency becomes 1 into what is full load kVA? 40. What is the power factor? 0.8 divided by again 1 into 40 into 0.8 plus 0.45 plus 1 whole square, because X is 1 and the full load copper loss is now 0.850. Please don't forget to change the unit. Fine. So here we get percentage efficiency to be, after calculating this, please pause the video and calculate the value by yourself. Okay, I have already calculated it, so it comes out to be 91.6%. So this is one answer. See, the very important point is you have to remember the equation. And you should know how to, read the question and get the values from the question. And then you just have to put the values. See, the numericals are very simple, but they are asked for 6 or 8 marks, which are very important for the subject, right? Yes. So let us go to the next part. Next says maximum efficiency. So we know that at X times, the efficiency is maximum. Okay, so we have to find out what is going to be the value of X now, because at full load the efficiency is not maximum. Okay, so we have to find at what value of X the efficiency is maximum. Okay, so in our earlier lectures we have studied that for the value of X is equal to square root the iron loss upon full load copper loss. This gives you the maximum efficiency. Now we have the values, don't we? Yes, we have. So it is, now see, now here you are not going to take 0.450, though the value are going to be the same, but then see here why we converted it to be kilowatt in case of iron loss, core loss, or say copper loss, because one unit was kVA, but here both are same. Right? So here we are not going to convert it. Always the units should be of the same order. Correct? So please be careful about this. So here the value of X comes out to be 0.7276. Okay, so for the value of this, efficiency becomes maximum. Fine? Yes. So what is the maximum efficiency? Now maximum efficiency is given by this. Now where did this come from? This comes from that for maximum efficiency, what is the condition? What is the condition? That copper loss should be same as iron loss. Correct? This was the condition. So we have already studied this equation also, but I am again and again telling you, okay, so that it registers in your mind. Now we shall put the values. The value of X is not 1 now, which was the case in earlier, section. Now here the value of X becomes 0.7276. 7276 into full load kVA remains the same, power factor remains the same, divided by again yes, now plus it has to be 2. Now what value of WI we are going to take? Is it going to be 450 or 0.450? Come on, this is kVA now, correct? So if this is kVA, we have to take 0.450. Fine. I hope you understood this concept. Yes, into 100. Okay. So after calculating this, I got the value of maximum efficiency to be 96.28%. Okay. Yes, so this is our answer. Now you compare this efficiency with the previous one. The previous efficiency was 96.1% and this is 96.28%. Obviously this has to be greater than that because this is maximum efficiency. Now suppose you get a smaller value, it means that you have committed mistake somewhere. It means that we have not done calculation properly. So these are few points wherein you need not check your answer with your classmate. You yourself can check your answer whether maximum efficiency is greater than the efficiency. It has to be. Correct? Yes. Now we shall go to the third part, which is the last part, and it says that the load at which the maximum efficiency occurs. So kVA of at maximum efficiency is given by this equation. Okay. So now we just have to put the values. So what is a full load kVA? It is 40. Secondly, you have 4. Now see. Yes. Again. Now, am I going to take 450 and 850 or 0.45? Because when I calculated the value of X in the second section, I use 450, 850. Now here, come on, tell me the answer. It is going to be 0.450 because here kV is there. So here we have K. Okay? Yes. So it becomes 0.450 upon 0.850. So the value comes out to be kVA of eta max, that is at maximum efficiency, comes out to be 29.1. So the answer is 29.1. Fine. Okay. So at maximum efficiency, kVA is 29.1. So here we shall end today's class. We shall meet in the next class with few more problems. Okay. See you.